the forces that rule our universe. General relativity describes the most familiar of those forces, gravity. But quantum mechanics describes three other forces. The strong nuclear force. That's responsible for gluing protons and neutrons together inside of atoms. Electromagnetism, which produces light, electricity, and magnetic attraction. And the weak nuclear force. That's the force responsible for radioactive decay. Every event in the universe, from the splitting of an atom to the birth of a star, is nothing more than these four forces interacting with matter. Albert Einstein spent the last 30 years of his life searching for a way to describe the forces of nature in a single theory. And now, string theory may fulfill his dream of unification. For centuries, scientists have pictured the fundamental ingredients of nature, atoms and the smaller particles inside of them, as tiny balls or points. But string theory proclaims that at the heart of every bit of matter is a tiny, vibrating strand of energy called a string. And a new breed of scientist believes these minuscule strings are the key to uniting the world of the large and the world of the small in a single theory.
The idea that a scientific theory that we already have in our hands could answer the most basic questions is extremely seductive.
For about 2,000 years, all of our physics, essentially, has been based on, essentially, we were talking about billiard balls. The very idea of the string is such a paradigm shift. Because instead of billiard balls, you have to use little strands of spaghetti.
But not everyone is enamored of this new theory. So far, no experiment has been devised that can prove these tiny strings exist.
Let me put it bluntly. There are physicists and there are string theorists. It is a new discipline, a new, you may call it tumor. You can call it what you will. They have focused on questions which experiment cannot address. They will deny that, these string theorists, but it's a kind of physics which is not yet testable. It does not make predictions that have anything to do with experiments that can be done in the laboratory or with observations that can be made in space or from telescopes. And I was brought up to believe, and I still believe, that physics is an experimental science. It deals with the results to experiments or, in the case of astronomy, observations.
From the start, many scientists thought string theory was simply too far out. And frankly, the strange way the theory evolved in a series of twists, turns, and accidents only made it seem more unlikely. In fact, even its birth has been turned into something of a myth, which goes like this. In the late 1960s, a young Italian physicist named Gabriele Veneziano was searching for a set of equations that would explain the strong nuclear force, the extremely powerful glue that holds the nucleus of every atom together, binding protons to neutrons. As the story goes, he happened on a dusty book on the history of mathematics, and in it he found a 200-year-old equation, first written down by a Swiss mathematician, Leonhard Euler. Veneziano was amazed to discover that Euler's equations, long thought to be nothing more than a mathematical curiosity, seemed to describe the strong force. He quickly published a paper and was famous ever after for this accidental discovery.
I see occasionally written in books that this model was invented by chance or was found in a math book, and this makes me feel pretty bad. What is true is that the function was the outcome of a long year of work, and we accidentally discovered string theory.
However it was discovered, Euler's equation, which miraculously explained the strong force, took on a life of its own. This was the birth of string theory. Passed from colleague to colleague, Euler's equation ended up on the chalkboard in front of a young American physicist, Leonard Susskind.
To this day, I remember the formula. The formula was and I looked at it and I said, you know, this is so simple, even I can figure out what this is.
Susskind retreated to his attic to investigate. He understood that this ancient formula described the strong force mathematically. But beneath the abstract symbols, he had caught a glimpse of something new.
And I fiddled with it, I monkeyed with it, I sat in my attic, I think for 2 months, on and off. But the first thing I could see in it was describing some kind of particles which had internal structure, which could vibrate, which could do things, which wasn't just a point particle. And I began to realize what was being described here was a string, an elastic string, like a rubber band, or like a rubber band cut in half. And this rubber band could not only stretch and contract, but wiggle. And, marvel of marvels, it exactly agreed with his formula. I was pretty sure at that time that I was the only one in the world who knew this.
Susskind wrote up his discovery, introducing the revolutionary idea of strings. But before his paper could be published, it had to be reviewed by a panel of experts.
I was completely convinced that when it came back, it was going to say, Susskind is the next Einstein, or maybe even the next Newton. And it came back saying, this paper is not very good, probably shouldn't be published. I was truly knocked off my chair. I was depressed, I was unhappy, I was saddened by it. It made me a nervous wreck, and the result was I went home and got drunk.
As Susskind drowned his sorrows over the rejection of his far-out idea, it appeared string theory was dead. Meanwhile, mainstream science was embracing particles as points, not strings. For decades, physicists had been exploring the behavior of microscopic particles by smashing them together at high speeds and studying those collisions. In the showers of particles produced, they were discovering that nature is far richer than they thought.
Once a month, there'd be a discovery of a new particle, the rho meson, the omega particle, the B particle, the B1 particle, the B2 particle, phi, omega. More letters were used than exist in most alphabets. It was a population explosion of particles.
It was a time when graduate students would run through the halls of a physics building saying, they discovered another particle, and it fit the theories, and it was all so exciting.
And in this zoo of new particles, scientists weren't just discovering building blocks of matter. Leaving string theory in the dust, physicists made a startling and strange prediction: that the forces of nature can also be explained by particles.
Now, this is a really weird idea, but it's kind of like a game of catch in which the players, like me, and me, are particles of matter.
And the ball we're throwing back and forth is a particle of force. It's called a messenger particle.
For example, in the case of magnetism, the electromagnetic force, this ball would be a photon. The more of these messenger particles or photons that are exchanged between us, the stronger the magnetic attraction.
And scientists